Hello and Assalamualaikum everyone. My name is Haikal and we are from group 2A of my team. Today we will present to you guys our IDP project, which is Integrated Reactor and Separation System for High Purity Nitric Oxide Production. So without further ado, let's move to the first part, which is Introduction of Reaction Engineering. Reaction engineering is a critical discipline in chemical engineering, focusing on designing and optimizing reactors to ensure the efficient and sustainable production. Our study centers on the catalytic oxidation of ammonia, a process essential for nitric oxide production. This reaction forms the backbone of nitric acid synthesis, a cornerstone of the chemical industry. The key challenge lies in the optimizing parameters like temperature, pressure, and reactant flow to maximize yield while minimizing undesirable byproducts. With global nitric acid production exceeding 100 million tons annually and growing application in medicine and industry, advancing this process is essential for meeting future demands. Next is the kinetic reaction. The primary reaction of ammonia oxidation involves ammonia reacting with oxygen to produce nitric oxide and water. The reaction follows third-order kinetics, with the rate proportional to the concentration of both reactants. A significant challenge is the side reaction, which is forming a nitrous oxide, which reduces NO yield and contributes to greenhouse gas emissions. Optimizing conditions like temperature and oxygen availability is key to maximizing NO production, while minimizing the undesirable product. Okay, move to the optimal catalytic system. Catalyst plays a crucial role in ammonia oxidation. The platinum-rhodium-palladium combination is the industry standard, with rhodium enhancing reliability and palladium reducing the nitrous oxide emission. Optimized design like the EcoCat system ensure the long campaign durations, minimize downtime, and improve overall process efficiency, making them indispensable for industrial scale nitrous oxide production.
Hello and Assalamualaikum everyone. So my name is Mohammad Amir Wafi. So next I will explain about the production capacity of the system. So our system operates at 80% ammonia conversion efficiency to ensure a high yield of nitric oxide. The initial ammonia flow rate is 11.74 kmol per hour, which will produce 5.5 kmol hour of NO after conversion. Since the plant runs 80,760 hours per year, the total annual production is 1,156.32 metric tons of NO. This production scale is ideal for medium-sized industrial application. By using advanced platinum, rhodium, palladium catalysts, efficiency can be further improved. Our system offers a balanced solution for high yield and cost-effective NO production. Next, we go to the type of reactor. So we compare two reactor types, which is plug flow reactor (PFR) and continuous tank reactor (CSTR). The PFR was chosen because it provides higher conversion efficiency per unit volume and better heat management for the highly exothermic reaction. While a CSTR offers a better mixing, it requires a much larger volume, making it less efficient. The level speed plot show that as conversion increases, the reactor volume grows significantly. A PFR optimizes the reaction rate while keeping the reactor size smaller and cost lower. In summary, the PFR is the best choice for ammonia oxidation, ensuring high efficiency, controlled heat management, and cost effectiveness. For reactor sizing, we calculated that the optimum PFR volume is 1.4432 dm3, while a CSTR will require 8.8526 dm3, making it much less efficient. So the key operating conditions were optimized in three. First one is temperature, which is 750 to 850 degrees Celsius for the best balance of reaction rate and efficiency. Second, the pressure need to be 1 to 2 atm to enhance conversion without slowing the reaction. And the last one, residence time, which is to optimize to achieve high conversion without unnecessary reactor expansion. So, the final reactor design is a PFR with a length of 50 meters, a diameter of 0.2 meters, and a volume of 1.57 meter cube. This ensures maximum efficiency with minimal cost. So, to conclude the reaction engineering part, our study successfully optimized ammonia oxidation for NO production. We confirmed that a 50-meter long PFR with a 20 cm diameter achieved 80% ammonia conversion and produced 171.55 kg per hour of NO. Our level speed plot analysis proved that PFR is the best reactor choice. We also identify ideal operating condition, which is 750 to 850 degrees Celsius temperature, 1 to atm pressure, optimized residence time. To improve the process, better catalyst, heat recovery, and advanced process control can be implemented. This step will make NO production more efficient, cost-effective, and sustainable for industrial application. So that's all for the reaction engineering part. So thank you.
Good afternoon, everyone. I'm Vvy. Today, I will be presenting our project for CFP2063 Separation Process 2. Medical grade nitric oxide (NO) is widely used in healthcare, particularly for respiratory treatments. However, industrial production introduced harmful impurities like NO2 and CO, which must be removed to meet the required 99.9 purity. Additionally, with the growing demands for MO in medical applications, a scalable and reliable purification process is essential. Our goal is to design a reactor-separator system to achieve 99.9% purification efficiency for nitric oxide. This will be accomplished using adsorptions and membrane separation techniques to ensure compliance with medical grade standards. To achieve this, we will apply principles from Chapter 1 on adsorptions and Chapter 4 on membrane separations. Nitric oxide is produced through the catalytic oxidation of ammonia using a platinum-rhodium catalyst. This reaction takes place in a plug flow reactor PFR at 800 degrees Celsius and 2 atm, following the primary reaction to produce NO and water vapor. Apart from that, a secondary oxidation reaction occurs, forming nitrogen dioxide. As a result, the system contains several impurities. First, nitrogen dioxide from NO oxidation. Water vapor, a byproduct of the primary reactions. Unreacted ammonia due to incomplete conversions, and unreacted oxygen, excess reactant from the initial process. Moving forward, we assume that all species in a system exist in a gaseous phase, allowing us to apply the ideal gas law for our analysis. The universal gas constant used in our calculation is at 0.314 kPa dm³ per mole Kelvin. Using the ideal gas equation PV equals to nRT, we can derive the molar concentration equation for each species, Ca equals to YAP of RT, where Ca is the molar concentration, Ya is the mole fraction of each species, P is 273.591 kPa, while T is 1073.15 Kelvin. By substituting this value, we obtain the molar concentration for each species, which are presented in the following table. These values are very crucial for designing an effective separation process to achieve medical grade purity. To achieve 99.9% purity of nitrogen oxide, we use a multi-stage purification process combining adsorption, condensation, membrane separation, and cryogenic distillation. The process starts with two adsorption columns. Column 1 remove unreacted ammonia through counter-current liquid phase adsorption. Column 2 eliminates nitrogen dioxide, reducing reactive impurities. Next, the gas mixture is cooled in a condenser to remove water vapor by bringing it below its dew point. This prevents moisture from interfering with later steps. We then remove excess oxygen using gas permeation membranes. These membranes allow O2 to pass through faster than NO, leaving behind a purified NO stream. For the final purification, the gas is cooled to cryogenic temperatures, -152 degrees Celsius, to separate NO from nitrogen and trace gases based on their boiling points. These steps ensure that the highest purity standard for medical and industrial applications. By integrating these four key purification steps, we efficiently remove all unwanted impurities, delivering high purity NO suitable for critical uses. Let us now explore the detailed specifications of each process.
Our goal is to achieve 99.9% nitric oxide purification efficiency for medical and industrial applications. Impurity like ammonia, nitrogen dioxide, water, and oxygen affect nitric oxide stability, so we use a multi-stage purification process to remove them. First, ammonia is removed using zeolite adsorption, following the Flemish isotope model. Temperature strain adsorption regenerates the zeolite achieve more than 90% of ammonia removal. Next, ion JSM5 adsorb nitrogen dioxide via chemsorptions. They follow the Langmuir isotope model, where adsorption happens in a monolayer. Pressure strain adsorption restores capacity, removing more than 95% of nitrogen dioxide and preventing oxidations. Water is removed by cooling the gas to 5 degrees Celsius, causing condensations. A knot of drum separates liquid water, eliminating more than 99% of water and preventing acidic byproducts. Oxygen gas is separated using membrane filtration, where oxygen diffuses out while nitric oxide is retained, reduce oxygen to less than 0.1%. Finally, cryogenic distillation cools the gas to 1020 Kelvin using different boiling points to insulate nitric oxide at 99.9 purity. This multi-step process ensures high purity nitric oxide.
Hi, I'm Willie. Next, I'm going to talk about the adsorption column design. The adsorption column design relies on selecting effective adsorbents for efficient contaminant removal. Natural azoates are chosen for ammonia removal via adsorption, ensuring easy regeneration, while ion exchange azoates target nitrogen dioxide through chemabsorption with ion active sites. To meet the required absorption capacity, a formula of mass of adsorbent equals to total impurity removed divided by adsorption capacity is used. As shown in the slides, 2,795.1 kg of adsorbent is used, while 675.1 kg of natural azoates for ammonia and 2,160 kg of ion exchange azoates for nitrogen dioxide. This optimized allocation maximizes pollutant removal while maintaining material efficiency. Next, we need to determine an appropriate isotherm to predict adsorption behavior. The Freundlich isotherm suited for heterogeneous surfaces that fits natural dilates with an N value of 1.82 and R-square value of 0.9977, confirming strong correlation and indicating favorable ammonia adsorption. For ion exchange dilates, the Langmuir isotherm, which assume monolayer adsorption on a homogeneous surface with high selectivity on nitrogen dioxide. These models ensure accurate adsorption predictions for an optimized system. Moving on to the MTZ design, where the mass transfer zone MTZ represents the region in the adsorption column where the concentration of the pollutant gradually decreases from its initial value to near zero. The calculation of MTZ is essential for designing an efficient column, ensuring that breakthrough does not occur prematurely and the adsorbent is effectively utilized. A few key parameters are designed based on our references. Through a field calculation, the breakthrough height is equals to 120 cm, where the unused bake height equals to 80 cm. By using this value, MTZ height is calculated and it is equals to 40 cm. To extend adsorbent lifespan and maintain efficiency, tailored regeneration methods are applied. For natural dilates, which we use to remove ammonia via desorption, we undergo thermal desorption to release adsorbed molecule with moderate heat. For ion exchange dilates, which can absorb nitrogen dioxide, chemical regeneration is required to break strong bonds and restore adsorption capacity. These methods reduce operational costs, enhance sustainability, and ensure long-term system performance.
Alright, so in conclusion, the separation process system effectively achieved high purity medical scale nitric oxide through adsorption, condensation, membrane separation, and cyclogenic distillation. Adsorption removed NH3 and NO2. Condensation removed moisture. Membrane separation reduced oxygen. And cyclogenic distillation ensure 99.9% purity. Natural geolites follow the Freundlich isotherm, while Fe exchange geolites adhere to the Langmuir isotherm, with an optimal mass transfer zone MTZ of 40 cm. Future improvements should focus on enhancing geolite's adsorption efficiency through structural and chemical modification for better impurity removal. That is all from us. Thank you so much.